Well, hello. This is Mrs. Wigton and Exploring Creation with Physical Science, 3rd edition, Module 12, Earth Science, Our Earth. All right, I'm going to turn the student notebook with me to page 358. We're going to dive right in. What is geology? Well, geology is the study of Earth, including its physical structure, its composition, history, and the processes that act on it. So it's anything to do with Earth, the way it's been made, and the history and things that happen to it. That's the best summary I can give you there. What are seismic waves and seismographs? Well, seismic waves are sound waves that travel through the earth and bounce back, hitting seismographs, which analyze the vibrations. So seismic waves are the sound waves, and the seismographs are the thing that measures those vibrations. Okay, moving on down. Look at all this doodling. Mrs. Wigton got distracted. Let's pause for a second. All right. What is the difference between the compositional layer of the earth and the mechanical layers? Include the different layers of each. So compositional layers would be the crust, mantle, and core. And the mechanical layers are lithosphere, asthenosphere, mesosphere, outer core, inner core. And they are determined by their physical properties. The compositional layers, the core, mantle, crust, are determined by their chemical makeup, what makes them up. So, so physical properties would be, I think, more of what they look like, and or where they're at, and chemical is what are they made of. Okay. So let's move down. Crust. Why is the crust the only section of Earth that we know really, really well? Well, it's the only section that we can actually observe directly. So that's why. Oh, looky here. Mrs. Wigton spilled water on her thing. Oh, now I smudged it too. Look at that. All right. Most of the rocks that make up the crust are silicates, which is silicon and oxygen. Silicon dioxide, or also known as silica, is the main component in sand and glass. There are two types of crust, the continental crust and the oceanic crust. So continental is obviously anything that's not ocean. It's underneath the land, and it can be thicker underneath mountains, and it tends to be thinner under oceans, but there's still the crust underneath both. The mantle. So we're getting a little bit deeper. Underneath the crust is the mantle. The mantle has different layers. Let's see here. So they've still got the oceanic, the crust here and here, but then we've got the moho. The moho is actually short for, I wrote it out here, Mohorovičic discontinuity. And they shorten it to moho, thankfully. And that moho is the separating, it's the dividing line between the crust and the mantle. Okay, so the crust, the mantle, and the moho is right between them. All right, and then we have mantle parts. We have the asthenosphere and the mesosphere. So those are the two parts of the mantle, astheno and mesospheres. Vocabulary. Plastic rock is rock that behaves like something between a liquid and a solid. For instance, oobleck, and the stuff that we made in class. All right, 361, we've got the mantle, and then, which we already looked at, and then we're going to deep dive into the core now. So just like we had the moho separating the mantle from the crust, which would be obviously right on the tippy top of this, right here would be the moho, then the mantle. Well, there's a dividing line between the mantle and the core, which both of these make up the core. And that is called the Gutenberg discontinuity. It does not have a cutesy name like moho. So this is not the printing press guy, but this is a different German, a different Gutenberg, this was named after. And then there's the outer core, which we know, and we'll get to in a minute, is liquid, and the inner core, which is solid, mostly solid, and in between the two is Lehman discontinuity. This was a woman this was named after. That was pretty cool. Lehman discontinuity. So that divides the outer and inner cores. And she was the one who discovered that. The inner core was solid. All right, what is pressure freezing? Well, heat normally makes atoms move away from each other and liquefy, except for water, but you add pressure and tons of it to the substance, and it becomes solid again. So we've got that heat making the this part liquid, and then but then there's so much pressure in the middle that here it's become solid. So that's what pressure freezing is. Why is Earth's magnetic field so important? Well, this picture is actually really a good picture of what's going on with the magnetic field. And I'll try to hold this still, sorry. It's probably because I'm so close. Maybe I could... Well, we're in focus, so we're going to keep it like it is. The magnetosphere, I like this word because it has the word "neato" in it. The magnetosphere is the other word for the Earth's magnetic field. And out here we have cosmic rays from the sun and the solar system coming out. This is not just all from the sun. And they are deadly. They would actually kill us if they could hit Earth directly. But the magnetosphere protects us. And if it was any weaker, it would not protect us. Any stronger, and it would deflect the cosmic rays and cause deadly magnetic storms. So, my goodness. I think God thought of every little tiny detail to make sure that we were safe and could survive on this planet. All right, we're on 362. Would water be subject to pressure freezing? Why or why not? Well, they explain in the thing that most things would do what happened with the pressure freezing. What happened at the core, and because the atoms tend to, when they get closer together, they would normally make a solid, not a liquid. But in water, it's one of the few compounds that its atoms, when they are closer together as a liquid, and then as a solid, like ice cubes, they expand. And so it's why if you ever fill up a glass jar with any kind of liquid, whether it's soup or even just water, it will, if you fill it up too far and don't leave enough room in that jar, it will crack and break overnight in the freezer. I've broken many a mason jars that way. So that's what happens. Describe the three main layers of Earth. All right, my fancy picture here. We've got the core. We have the solid inner core, liquid outer core, mantle, which is hot solid rock, and the thin crust made of rocks and soil. There's the oceanic and the continental crusts, the one that's under the part that's under the ocean, the part that's under the land. That's it in a nutshell right there. All right, moving on, 363. Sediment we're going to start with the vocab. Small, solid fragments of rock-like gravel, sand, silt, mud, or clay. Have you ever gone to a kind of a rockier beach, or just beside a creek even? That's even probably more accurate. and just dug down with your hand and picked up some of the sediment that's sitting there. I want to use the name, but that is it. You're going to see in it tiny little bits of gravel, sand, silt, mud, clay, all in there. And it loves to sit beside a creek or even a river, and that's sediment. All right. Sedimentary rock. This particular one is sandstone in the picture. Layers of sand and mud build up, and the weight compresses the layers below. And in this tiny little spaces between the sediment, a chemical reaction happens in the water there, hardening and binding the grains of sediment together. Isn't that awesome? That's how sedimentary rocks are come about. If you ever wondered, where do baby sediment rocks come from? Here we go. Igneous rocks. Remember, there's sedimentary, igneous, and metamorphic. Okay, that's really important. You know those 3 types of rock: sedimentary, igneous, and metamorphic. This particular one in the picture is granite. You can see little crystal flecks in it. Magma is hot liquid underground. Sorry, hot liquid rock underground. And when it reaches the surface of Earth, it's called lava. You see crystals because as it cools, it forms crystals. If the air, the ocean cools fast, like in lava, then the crystals will be small. If the magma cools slowly underground, the crystals can be big. Like, I'm assuming, I'm not sure it's an igneous rock, but I can only imagine. Like a diamond. You think of all those beautiful big gemstones that are underground. Well, they cooled slowly. And that's igneous there. All right, metamorphic. Metamorphic, when you think of metamorphic, I want you to think of the word change. Because to morph and just from one thing to another is to change, okay? This particular rock picture is schist. Heat or pressure can change igneous and metamorphic rocks into something, igneous and sedimentary rocks into something new. That was a typo on my part. My apologies. So, igneous and sedimentary. We're videoing.
Sorry.
You can talk though.
I was just flexing.
Happy to listen to you in a minute. Okay. Heat or pressure can change igneous and sedimentary rocks into something new, and if they do that, it'll change their structure and other elements, and basically they will become a metamorphic rock. If they change their structure, they are now a metamorphic rock. So cool, huh? All right, minerals. So minerals are different from sedimentary, igneous, and metamorphic rocks. Okay, those are the main 3 types of rock. We have solid, naturally occurring, inorganic substances that have a definite chemical composition and crystalline structure. Okay, so as you read, we're going to look at these examples. So I already read ahead for you. All you have to do is follow along. All right, we got some pretty pictures here. Crystal structure. This is how they know and identify minerals. So just to be clear here, okay? Specific geometric shape is what a crystal structure would be. Any size. For instance, quartz always have 6 sides. Like that's a picture of quartz. Garnets can form up to 12-sided crystals. I wondered why it was up to, but I think it's because it takes time to make that many, and so you can't assume every garnet is going to have all of those 12 sides completely developed. Halite makes cubic crystals, and some make threads or sheets of crystals. Isn't that awesome? Color. So another way they might identify a mineral is by the color of it. So this one here is pyrite. This was, I believe, that fool's gold. It's really sparkly, and it's tricked a lot of people into thinking they found gold in the river bed, but they didn't. and sulfur, which can be very stinky if I heat it up, but it's very yellow. So some minerals can be identified by their color, but not all. For instance, quartz crystals, like in this picture down here, can come in multiple colors. As you can see two right there. So you may not be able to tell by its color because it might come in multiple colors. Some are always the same though. Streak. Okay, when you hear streak for identifying a mineral, what you want to think of is a porcelain tile, like these in this picture right here. How about I get it focused for you? And they're unglazed porcelain tiles, and you're going to take a rock of some sort, ideally a mineral, and you're going to streak the porcelain down with it, and we'll see what color comes out. And it might match the color of the rock, it might not. It might be totally different. It can help in identification. Luster. How shiny is it? Sorry, I've got a little bit of sunshine and it's hard to see right there. There we go. How shiny is it? Sulfur is resinous. So here's a picture of sulfur. They call that resinous for its luster. Other adjectives they might use for luster are earthy, silky, pearly, adamantine, which is sparkly, and vitreous. Vitreous is glassy like quartz. This is galena or galena, probably galena in this picture right here. It's pretty vitreous. It's pretty glassy looking. All right, hardness. A mineral's ability to resist being scratched is what hardness is. A hard mineral can scratch softer minerals, but softer minerals cannot scratch a harder one. All right, let's look at a picture about this one because this is a little bit of, it's not that hard to understand, but I think it's a really neat concept. So this is all about hardness here. Let's see if I can focus right. Suppose you had a substance that you thought was gold. You find that calcite scratches it. There's calcite right there. Calcite scratches it, but gypsum does not. Well, gold, they happen to already know, has a hardness of 2.5 right in the middle. So your substance is most likely gold, since calcite has the hardness of 3, gypsum has the hardness of 2, and that puts gold right in the middle. So you would just take an unknown substance, and you would, if you had all of these available to you, you could scratch them with what you have, and you could find the hardness level and match it up on with what's its known hardness rating. So it helps because they already know it has these have consistent hardness levels. Isn't that cool? Fracture and cleavage. So fracture is how a mineral breaks apart, and cleavage is when a mineral breaks along a well-defined plane or flat surface. Here's a picture. So that's an interesting picture. I think of shale when I go to the beach. Back in we used to go to. It wasn't really a proper beach, but it was a lake in West Virginia. We would find these shale rocks, and you could just split them apart, and that would be the shale, the cleavage. I would know it was shale because of the way it broke along that plane and that flat surface and made these sheets of shale. So it's pretty cool. All right, what is a mineral? Minerals are naturally occurring inorganic solids with a regular crystal structure and a definite chemical composition. So they're natural, and they've got a crystal structure and a definite chemical composition. That's hence their hardness level and the colors they leave behind and things like that. Rocks are sedimentary, igneous, and metamorphic. Got to remember those, okay? Sedimentary, igneous, metamorphic. Okay, suppose you've got 2 mineral samples. They both have the same color and luster. What tests could you decide could you do to decide if the two samples are the same mineral? So you could do a streak test, you could check their crystal structure, you could do a hardness test, and you could check their fracture and cleavage. Those are the 4 tests that are left besides color and luster. So any of those would be acceptable. Streak test, crystal structure, hardness test, and fracture and cleavage. All right, we're on page 367, rock cycle. A series of processes in which forces inside and on Earth cause rocks to continuously change from one type of rock to another. So what's causing rocks to change from one thing to another? These processes. All right, so we've got these right here. I've got a reference to look in the book on this. But we'll look real quick here. We've got, these are the processes: cooling, weathering, erosion, deposition, heat and pressure, compaction and cementation. That's hard to say, and melting. So those are some of the different things that can happen. And we're going to look at page 445 real quick. Oh, this is good. I like this. Okay, I get it now. All right, use this figure to explain. All right, so I'm going to read you a little bit here. In one pathway of the rock cycle, the granite rock is worn down by weathering and erosion into sand. So we got the weathering and erosion down into sand, okay? Think about a rock on a mountain and the wind blowing it down, and it just kind of eroding or getting smaller and smaller until it's sand. Perhaps rain and wind carry the sand to a river, which transports the sand to the ocean and deposits it as sediment. So here we go, deposition. That's the depositing it as sediment. Eventually, layers of sediment are deposited on top of each other. See the layers? And as they become compacted, this is the pressure, cementing together to become part of the sedimentary rock, sandstone. So there's, I'm sorry, I wasn't showing it over here. So we've got our sedimentary rock, okay? Right there. If the sandstone is pushed deep underground, this is where the heat and pressure can cause it to undergo metamorphism and form the metamorphic rock quartzite. So it goes deep enough. Remember, it gets hotter as things go down into the earth, and that heat and the extra pressure from all the weight above. So first it turned into sedimentary rock without the pressure so much, just a little bit. I mean, there was some compaction going on for sure, but then it metamorphosizes into a metamorphic rock here. It changes into a metamorphic rock because of the heat and pressure from it being so deep. But even this doesn't even end the rock cycle. The quartzite could be pushed to the surface and be exposed to weathering and erosion, which again causes the rock to form sediment. It could go around again, just like we just did right here, and stay over here. Or it could be heated past its melting point and become magma. Go over this way. It becomes magma, which upon cooling, as it rises to the surface of the earth, is lava. So as it hits the surface of the earth, the magma becomes lava. It forms another igneous rock. Isn't that awesome? So I guess those weren't mountains in this picture. Those are actually volcanoes. But yeah, so that's more and more changing. So all of those changes complete the rock cycle. So we've got the weathering, melting, the transportation, deposition, all of those listed there. We got others are cooling, compaction, cementation, heat and pressure, melting. Okay, so all that's in there. Very cool. All right, move that over there. All right, we're on 368, hydrosphere. I think we could break this one apart. Sphere is round, hydro is water. Well, what is a hydrosphere? The sum of all water on a planet. So for our Earth, this is, I wrote down some numbers here for you, and I'm sorry this is so bumpy today. Don't know, I'm not really shaking. Just have a shaky camera today. All right, so oceans make up 97% of all the water on our personal planet Earth. Did you know, just a side note here, that big E Earth means planet Earth and little e Earth means like ground dirt? Isn't that cool? So if you are writing and you're writing a paper and you want to reference our planet Earth, make sure it's got a big E. But if you're talking about sitting down on, well, that doesn't sound right either. It sounds like it could be talking about the planet. He picked up some earth in his hand. Well, that would be little e Earth. Okay, back to it. So on our planet Big E Earth, we have 97% salt water oceans. Why did God give us so much salt water when we can't even drink it? Why? Well, he's got a plan with all this stuff. Let's look at the rest of the water. Glaciers, icebergs, they make up 2% of all of the water on Earth, and that happens to be fresh water. All of the rest of these are fresh water. Groundwater is water that is underground. It makes up 0.7%. Surface water, which is your typical lakes and creeks and rivers, is 0.009% of all of Earth's water, also fresh water. Soil moisture is 0.005%, so in the dirt and stuff like that. And atmospheric moisture, the water that's in the air is 0.001% of all of the water on our planet. So I thought that was really interesting. So what is groundwater? I just told you. Does anybody remember? It's underground water. That's what that is. Where do you find surface fresh water? Lakes, ponds, rivers, streams, and creeks. So we are cruising. All right. List 3 key facts you should remember about Earth's water supply. Well, we just went over these, but in a more succinct way, you should know what these are. Most of Earth's water supply is found in the oceans as saltwater. Most of Earth's fresh water supply is in icebergs and glaciers. Think Antarctica and the Arctic. What is it called? North Pole. So the Arctic Circle, the North Pole. And the third fact you need to know is that the largest liquid fresh water is groundwater or underground water. Good. All right. Vocab. Hydrologic cycle is also known as the water cycle. That's when water changes from one water source to another. And there's a big picture we'll look at in just a minute. Transpiration. Now, don't get confused. This is not transportation or respiration. It's a mixture of those words. Transpiration is the evaporation of water from plants. And we'll look at a picture of that in just a minute. Precipitation is water falling from the sky, such as rain, snow, sleet, and hail. That's precipitation. So if you ever listen to the weather person on TV or on the radio, they'll say, oh, we've got a 50% chance of precipitation today. Well, that's about the whole of spring and fall in Oregon. It's 50-50 every day. All right. The hydrologic cycle or the water cycle. Anytime you say hydro, I want you to say water. Okay. All right. So we're going to start with, where should we start? Let's start with precipitation because it's easiest. All right. So we got rain coming down. Precipitation. They've got a 100% chance of precipitation today. Okay, it's coming down, and some of it goes onto the earth, and some of it goes onto the water, and then the sun comes out, and that water evaporates. Some of it straight out of the water, evaporating, and some of it transpirates out of the trees and anything that's a plant life. So that's transpiration. Okay, and that puts that water back into the atmosphere. And the water vapor forms clouds by the process of condensation. So we've got condensation. You should have done a cool experiment on if you're in challenge 1 on condensation, which, by the way, one of the kids in my class, 2 of them are Boy Scouts, and they told me they do a condensation experiment all the time with when they go out camping. They make sure that all the Boy Scouts know how to turn salt water into fresh water, so that if that's the only source of water that they have, they know how to basically get that water to condense on something like a lid, and then they can catch it and drink it, because they can evaporate the water out of the salt water and leave the salt behind. Isn't that awesome? So that is funny that they already knew what was going to happen with that. All right. Explain the ways that water can leave the soil. Transpiration depletes soil moisture. Also, that's where the transpiration, this is that. It takes the moisture out of the soil, as well as a groundwater flow takes moisture from the soil and feeds it into lakes and rivers and streams. So groundwater flow and transpiration is where the water in the soil goes. All right. How does water get back into the soil? Well, gravity causes water in the clouds to fall as rain, snow, sleet, or hail. So right here. So the condensation made the clouds. Well, gravity brings that precipitation down back into the earth, into the soil. All right, what is surface runoff? This is just a good, very grown-up term to know. Surface runoff. Surface runoff is water that runs along the surface of land into a body of water. So not all of it gets absorbed back. Sometimes some of it just rolls alongside along the ground, and with gravity rolls down into a creek or a lake or a river or back into the ocean. So that's what happens. And look, we are so fast. We just got ourselves completely finished here with the first half of Module 12. So it looks like Mrs. Wigton's got some work ahead. All right. Thanks for, I want to say bye. Thanks for sticking with me today. Take care. Bye-bye.